Now let us see few more questions. The first question, two wires of same material and same length have radii R1 and R2 respectively. You need to compare their resistance and their specific resistance. So how you are going to compare their resistance and specific resistance? You have two wires. Suppose there are two wires, wire A and B. Okay, suppose. Now they have radii R1 and R2. One has radii R1. So what you can say about the area of A? Area of A will be pi R1 square and area of B will be pi R2 square. Okay, you got the area. Now they are of the same material. They are of the same material, that means they share the same specific resistivity. So if rho 1, that is the resistivity of A, is rho, rho 2, that is the specific resistivity of B, will also be rho. So they share the same resistivity. Also the length are same. Okay, so all these factors are given to us. We need to compare the resistance. So first let us find out R1. We know the formula for R is rho L by A. So it will be R1 will be rho 1 L1 by A1. Rho 1 is rho, L1 is A, and A1 is pi R1 square. Okay. Similarly, let us find R2. R2 is rho 2 L2 by A2. Rho 2 is rho, L2 is L, and A2 is pi R2 square. You have found both? Now compare, since you need to compare them. How you are going to compare? R1 by R2. R1 we got rho L pi R1 square. And R2 we got rho L pi R2 square. You see rho, L, pi are getting cancelled out. So you are left with R2 square by R1 square. That means, what is the answer? The answer is R2 square is to R1 square. Okay, clear? You can see. Now the second part says their specific resistance. What is specific resistance? This resistivity. So we can easily see that rho 1 is also equal to rho and rho 2 is also equal to rho. So if we compare rho 1 and rho 2, if we compare rho 1 and rho 2, which is rho by rho, so what are we getting? 1 is to 1. Okay, clear this part? Okay, now let us enter into the next question. The next question says, a given wire of resistance 1 ohm is stretched to double its length. Okay, what will be its new resistance? Okay, a given wire of resistance 1 ohm, that means initially we know the value of the formula for resistance is rho L by A, and this is equal to 1 ohm as per the question. It's given. Okay, it is stretched to double its length. That means we have a new set of length. Okay, let us write it here. New length L dash, double of the original length L. Original length was L, so double of L. Okay, now if the length is doubled, what will happen to the area of it? Area will also get, what will happen to the area of it? The area will also get doubled, right? You are doubling the length, you're stretching, sorry, if you're stretching it, because you're stretching to double its length, then in that case the wire will become thin. I'm really sorry. So in that case area will become half, it will decrease. So the new area A dash will be equal to A by 2. Now you replace it in the value of new resistance. So R dash is equal to, since the wire is same, so rho will remain same. In place of, this will be L dash, A dash. So rho, in place of L dash we will write 2L, and A dash we will write A by 2. Okay, this 2 will go up, so we will get 4 rho L by A. Now we know the value of rho L by A is 1. So how we are writing? 4 into 1, that is 4 ohm. This is our answer. This is the new resistance. Okay. Now let us see our last question. The last question says that what length of copper wire of specific resistance 1.7 into 10 to the power minus 8 ohm and radius 1 millimeter is required so that its resistance is 1 ohm. So what all is given to us? Given to us is the specific resistance. We'll write the values. Okay, so initially specific resistance rho 1.7 into 10 to the power minus 8 ohm is given to us. Okay, next what is given to us? The radius, which is 1 millimeter. Again, this is not in the SI unit, so you have to convert it to meter. How you are going to convert it to meter? By dividing it with 1000. So 1 by 1000. You can write it as 10 to the power minus 3 meter. Okay, so this is my radius. Now what is required to find? We have to find the length, and resistance is also provided to us. The resistance is equal to 1 ohm. Okay, we know the formula. What is the formula? R is equal to rho L by A. We need to find L. So we will make these L the subject of formula. So we will be left with L is equal to R A by rho. Okay, now place all the values. R is 1. Acha, area is pi r square. So pi 22 by 7, or you can also take 3.14 into pi r square into r 10 to the power minus 3 whole square. Okay, and then you have the specific resistivity. The specific resistivity is 1.7 into 10 to the power minus 8. So if you are going to calculate this, what are you going to get? What are you going to get? You will get a value of 184.7. It's a length, so meter. Please do this calculation and check it once. So this is our answer. The next topic is electromotive force, terminal voltage and voltage drop. Okay, we'll understand them one by one. First, let's see electromotive force. To understand electromotive force, first let us see what is the definition for electromotive force. So as per the definition, when no current is drawn from a cell, that is when the cell is in open circuit, that means when you are not using the cell, the PD between the terminals of the cell is called electromotive force. In short, we write it as EMF, electromotive force. Okay, so what does the definition says? The definition says that the potential difference between the terminals of the cell or the battery which you are using when the cell is not in use, when it is in an open circuit, when no current is drawn from it, then the potential difference between the terminals of the cell is called electromotive force. For example, you see we have a cell drawn here. In this cell we have the electrolyte as a dilute sulfuric acid as the electrolyte, and for the electrodes, that means the anode and the cathode, we have the copper and the zinc. Okay, so electrodes used are copper and zinc, and the electrolyte used is dilute sulfuric acid. You see, this is the positive terminal, this is the negative terminal, and you see the circuit is not complete. It is an open circuit. That means the cell is not in use and there is no current drawn from the cell. So in this case, the potential difference between these two terminals is given as the EMF E. EMF E. Actually, this symbol is called epsilon. epsilon. Okay, so for EMF we use the symbol epsilon. Now let us see what is terminal voltage. If you see the definition of terminal voltage, you see what is there? When current is drawn from a cell. In case of electromotive force, when no current is drawn. In case of terminal voltage, when current is drawn from a cell, that is when the cell is in a closed circuit, that means when we are using the cell, then the PD between the electrodes or the terminals of the cell is known as terminal voltage. That means again the PD between the two terminals, that is the positive terminal and the negative terminal, when the cell is in use. Okay, when the cell is used for drawing current, then the PD will be known as terminal voltage. So you see we have a diagram here. Again we are using dilute sulfuric acid as an electrode, copper and zinc, dilute sulfuric acid as an electrolyte, copper and zinc as electrodes, and now you see it's a complete circuit. Okay, it is a complete circuit, it is a closed circuit, and in this closed circuit the potential difference between these two terminals is known as terminal voltage. Okay, we can also say about electromotive force. Coming back to electromotive force, we can also say that when a cell is connected in a circuit, now you are connecting that cell in a circuit. Okay, current is flowing from the cell. Why the current is flowing? Because the cell has an EMF. That EMF provide energy for the charges to flow. Okay, so we can also define it as EMF equals to work done per unit charge. That means work done in taking a test charge Q around the complete circuit. Around the complete circuit means what? Around the complete circuit means both inside the cell and outside the cell. Inside plus outside the cell. Okay, so in the complete circuit. Now coming to terminal voltage. Terminal voltage is given by capital V, and capital V is equal to what? W dash by Q. Now what is W dash? W dash is the work done in carrying a test charge Q only outside the cell. Only outside the cell, not inside the cell, just as it was for electromotive force. Electromotive force, work done in carrying unit positive charge both inside and outside the cell, whereas terminal voltage, work done in carrying unit positive charge only outside the cell. Okay, up till here it is clear. Now coming back to voltage drop. What is voltage drop? Voltage drop is given as small v. Small v is work done, small w by q. And what is small w? Work done in carrying a test charge q through the electrolyte outside the cell. Through the electrolyte outside the here it will be inside the cell. Inside the cell. Through the electrolyte inside the cell. Okay, so here we have three kinds of work done, right? Number one, work done in carrying test charge around the complete circuit, that means both inside and outside the cell. Then we have work done in carrying test charge only outside the cell, and then work done in carrying a test charge inside the cell. Okay, so this is all about electromotive force, terminal voltage and voltage drop. Now let us see the relationship between electromotive force and terminal voltage. Next we will do relationship between EMF and terminal voltage. Relationship between EMF and terminal voltage. Okay. To this first we will start with the law of conservation of energy. All of us by now knows the law of conservation of energy. So by the law of conservation of energy, what do we mean? We mean that energy can neither be created nor destroyed. It is just transformed from one form to the other. That means the total energy, the sum total of all the energies is constant, remains constant. Okay, so by the law of conservation of energy, can we say capital W is equal to W dash plus small w. Work done in carrying unit positive charge through the entire circuit, through the complete circuit, that means both outside and inside the cell, is equal to work done in carrying unit positive charge outside the cell plus work done in carrying unit positive charge inside the cell. We can say this W is equal to W dash plus small w. Okay. Now if we divide this equation, first mark this equation as equation 1. Okay. Now if we divide this equation, dividing equation 1 by Q on both sides, what do we get? What do we get? We get W by Q is equal to W dash by Q plus small w by Q. Now we have already done W by Q. If you refer, go back to the video. If you go back into the video, you see we have done that W by Q is the EMF of the cell. W dash by Q is the terminal voltage and small w by Q is the voltage drop. Okay, so we get the relationship. Okay, how do we get this relationship? You can write it here. We know capital W by Q. Capital W by Q is the EMF. W dash by Q is the terminal voltage and small w by Q is the voltage drop. EMF, terminal voltage, and voltage drop. Okay, you can also write this as terminal voltage is equal to EMF minus voltage drop. From here what you conclude? That terminal voltage will always be lesser than the EMF. Okay, so when current is drawn from a cell, when current is drawn from a cell, its terminal voltage is less than its EMF. Okay, and by what amount it is less? By an amount equal to the voltage drop. Okay. Our next topic is internal resistance. Okay. We have already done resistance. What is resistance? What do we know about resistance? We know resistance is the obstruction offered to the flow of current, right? That was the resistance in the circuit. Okay, that was the external resistance. We also have something that is called internal resistance, and it is denoted by the symbol small r. What is internal resistance? If we go by the definition, internal resistance is the resistance offered by the electrolyte. It is the resistance offered by the electrolyte. Offered by the electrolyte. Where is this electrolyte? Inside the cell. So the resistance offered by the electrolyte inside the cell to the flow of current. Okay, this is internal resistance. Now how do we show it mathematically? We know that inside the cell, what is the potential drop? What do we have as a potential difference? We have the potential drop, right? We just did voltage drop. So voltage drop is given by small v, and current is flowing, suppose I current is flowing through the cell, and R is the resistance. So according to Ohm's law, we know that V is equal to I into R. Okay, so what is V? V is the voltage drop, I is the current, and R is the internal resistance. Okay, so V is equal to I into R. How will you represent the internal resistance of a cell? So internal resistance of a cell, you can represent it in this way. Suppose this is the cell and it has some internal resistance. So we just draw a small resistance like this, and we just enclose it in a dotted box. Okay, so this is the cell and this is its internal resistance. Okay. Now let us find the relationship between EMF, terminal voltage, and internal resistance. So how we are going to do that? For that, first we will need a circuit. So let's see. So let us draw a circuit first. Okay, this is my cell which has EMF and an internal resistance R. Okay, now this cell is connected to an external resistance, capital R. Okay, my circuit is complete. What we need to do, we have to find the relation between EMF, comma, terminal voltage, and internal resistance. Okay, we have to find the relationship between EMF, terminal voltage, and internal resistance. Okay, for that we consider there is a cell. Let there be a cell of EMF E. Okay, and internal resistance R. EMF E, internal resistance smaller. Okay, and it is connected across an external resistance, capital R. So external resistance, capital R. Okay, all these three things are given to you, and you can also see it in the circuit diagram. Now if you see the circuit, can you calculate the total resistance of the circuit? What will be the total resistance? What you can say about the total resistance of the circuit? You see, there are two resistors, capital R and small r. So the total resistance of the circuit will be R plus R. So capital R plus small r. This is the total resistance of the circuit. Okay. Now let us find the current drawn from the circuit, from the cell. Current drawn from the cell. So what will be the formula for current drawn from the cell? We know according to Ohm's law, the current I is equal to V by R, right? Current I is equal to V by R. So here current I will be equal to EMF of the cell by total resistance. Okay, so EMF of the cell, what we have? E, and total resistance R plus R. We got the total current. Okay, from here, since we want to find the relationship between EMF, terminal voltage and internal resistance, EMF, terminal voltage and internal resistance, let us make EMF the subject of formula. So if we make EMF the subject of formula, what we get? I, we take it to the left hand side, R plus R. Okay, we got the EMF, right? Now next we want what? Terminal voltage. So what will be the terminal voltage? Terminal voltage, again it is a potential difference. Terminal voltage is also a kind of potential difference. So terminal voltage of the cell is given by, we have done, it is given by capital V. So current in the circuit, according to Ohm's law, it is I into R. So current in the circuit is I, and resistance of the circuit, that means the external resistance, the resistance of the circuit, not of the cell. So the circuit is capital R. So V is equal to IR. We got the potential drop as terminal voltage as well. Now next, what do we want? Internal resistance. So for internal resistance, let us calculate the voltage drop. Voltage drop, where the voltage drop occurs inside the cell. So voltage drop is due to the internal resistance. So voltage drop due to internal resistance. Okay, so this voltage drop is given by small v. So small v is equal to total current flowing is R, and due to internal resistance is small r. So basically we want to find internal resistance. So make internal resistance the subject of formula. So this will be equal to V by I. All the three datas are known to us. Okay, so now can I write in this, it is what? Small v by capital I. Now can I write small v is equal to E minus capital V? We have done it before. Okay, if you want to check, we can check it once that we did this. We have done the relationship. You see, we have done it. Capital V is EMF minus V. So if you want to find small v, it is again capital E minus EMF minus capital V. Okay, so using that concept, small v is equal to EMF minus terminal voltage by I. Also we can write in place of I, can I write V by R from here? If you make I the subject of formula, so can I write capital V by R? Because I don't want current. Okay, I don't want current in my relationship. So can I write V by R? Okay, now can I take R on the numerator side? So entire thing becomes this. So this is the relationship. You can also write it as EMF by V minus V by V becomes 1 into R. Okay, so basically what is the relationship? We wanted to find the relationship of EMF, terminal voltage and internal resistance. So what is the relationship? Internal resistance R is equal to EMF by terminal voltage minus 1 into the external resistance R. Is it clear to all of you? You can go through the entire thing, and if you have any problem, you can ask me in the class. Now there are certain factors that affect the value of internal resistance. So what are those factors that affect the value of internal resistance? So our next topic is factors affecting the internal resistance of the cell. Okay, so excuse me, what are the factors affecting the internal resistance of the cell? There are four factors that affect the internal resistance of the cell. Number one, the surface area of the electrodes. The surface area of the electrodes. Okay, how it depends on the surface area of the electrodes? Larger the surface area, less will be the internal resistance. That means they are inversely proportional. The internal resistance is inversely proportional to the surface area of the electrodes. Number two, it depends on the distance between the electrodes. The distance between the electrodes. Okay, and how does it depend on the distance between the electrodes? The greater the distance, the greater will be the internal resistance. That means it is directly proportional to the internal resistance is directly proportional to the distance between the electrode. The greater will be the distance of the electrodes, the greater will be the internal resistance of that cell or battery. Number three, the nature and concentration of the electrolyte. The nature and concentration of the electrolyte. And how it depends on the nature and concentration of the electrolyte? The less ionic the electrolyte or higher the concentration is on the higher side, then the internal resistance will also be more. And finally, the fourth factor, that is the temperature of the electrolyte. And how it depends on the temperature? Greater the temperature, lesser will be the internal resistance. That means it is inversely proportional. My internal resistance is inversely proportional to the temperature of the electrolyte. Greater the temperature of the electrolyte, lesser will be the value of internal resistance. Greater the temperature of the electrolyte, lesser will be the value of internal resistance. Now, there are two types of combinations of resistors. That means resistors can be arranged in two ways. Okay, that is in series and parallel. So the topic is combination of resistors. Combination of resistors. Okay, so what are the two possible combination? Series and parallel. First we will do series. Okay, now combination of resistors in series. Number 1, combination of resistors in series. Here we need to find the equivalent resistance. If we combine the resistors in series, what is the total resistance of the circuit? Okay, so for that, let us consider a circuit having resistances in series. Let there be 3 resistances in series, R1, R2, R3. 3 resistors having value R1, R2 and R3. This is the battery, and you can use a key or a switch. Okay. Let us mark the terminals. A, D, the terminal of the resistor R1, AB, BC, and for R3, CD. Okay. Always remember 2 points about the resistance connected in series. About the resistors connected in series, always remember 2 points. Point number 1, the current has a single path for its flow. What does it mean? The current has a single path for its flow. It means that same current will pass through each resistor. Same current is going to go through R1, the same current will go through R2, and the same current will go through R3. Okay, for example, this is my battery, and we know current will come from the positive terminal. So I current comes out from is drawn from the cell. This I current goes through R1. The same current goes through R2 and the same I current goes through R3 in this way. Okay, so point number 1, same current goes through all the 3 resistors. Number 1. So, and the point number 2, the potential difference across the entire circuit is equal to the sum of the potential difference across individual resistor. Now what does this mean? You see, this is R1, this is current I flowing through R1. So potential across this resistor, you can write it as V1. Okay. Similarly, potential across this resistor, you can write V2, and potential across this resistor, V3. The potential across each resistor will be different. Why? They have same value of current, but the resistances are different. And we know what is potential difference. It is the product of current and resistance, I into R. So this will be I into R1. This will be I into R2. This will be I into R3. So let us consider, and also you see, when the terminals are different, then potential differences will be different. For example, the resistance R1 has terminal AB, the resistance R2 has terminal BC, and the resistance R3 has terminal CD. So all the resistance have different terminals. Okay, so therefore they have different potential differences, and this the total potential difference across AD will be the sum of the individual potential differences. That means the total potential difference V will be equal to V1 plus V2 plus V3. Okay, now let us take out the expression for equivalent resistance. How we will take out the equivalent resistance? First of all, we will consider that I current is drawn from the cell. So I is the current drawn from the cell. I is the current drawn from the cell. Now by Ohm's law, let us find the PD. So PD between A and B, terminal A and B. Can I write it as VA minus VB, which we have given the name V1. So V1 is equal to I into R1. Okay. Similarly, PD between B and C will be VB minus VC, which we have given the name V2. So V2 is equal to I into R2. Okay. Similarly, PD between C and D, that is VC minus VD, which we have given the name as V3. So V3 is equal to I into R3. Okay. Now, total potential, how we will get? Remember the second point I said about resistance connected in series. I said that the total potential difference will be the sum of the individual potential differences, right? So, total potential difference here, first let us write down the expression for it. Total PD across A and D, we can write it as VA minus VD, which will be I into total resistance. So total resistance here are total resistance in series. Okay, I into RS, because the resistance are connected in series, so I have written it as RS. Okay, now total PD equals to V1 plus V2 plus V3. Okay, so what do we get? V is I into RS, V1 is I into R1, V2 is I into R2, and V3 is I into R3. Now if you take I common, so R1 plus R2 plus R3, I and I will get cancelled out, so you are left with equivalent resistance in series RS is equal to R1 plus R2 plus R3. Okay, so this is the formula for combination of resistance in series. Now let us come to combination of resistance in parallel. Combination of resistors in parallel. Okay, again you need to remember 2 points of resistors connected in parallel. What are the 2 points? Point number 1, the potential difference across each resistor will be same. So to understand this, first let us draw the circuit. Okay, so let us draw the circuit for this. I am connecting 3 resistances in parallel. Okay, R1, R2 and R3. I have connected them in parallel. Like this. Okay, so they share the same terminal AB. You see in the figure, R1, one terminal is A, the other terminal is B. R2, one terminal is A, the other terminal is B. R3, one terminal is A and the other terminal is B. That means they all have the same 2 terminals, A and B. And hence the potential difference across each resistor will be same, which we can write it as VA minus VB, say V. That will be same across R1, R2 and R3. Point number 1. Point number 2, different current will flow through all the resistor and the total current will be the sum of the current flowing through the individual resistor. What does this mean? Now this is the battery. Suppose I current is coming out of it. Okay, this I current will enter into the circuit. It will see 3 paths. How many paths? 3 paths. Now this I current cannot flow through all the 3 paths simultaneously. So what it will do? It will divide into 3 parts depending on the amount of resistances in the circuit. So suppose I1 is going through R1, I2 is going through R2, and I3 current is going through R3. So it divides itself into 3 parts, and the total current is equal to I1 plus I2 plus I3. You can write I is equal to I1 plus I2 plus I3. Okay, now let us find the expression for the equivalent resistance. Okay, one thing is clear, I is equal to I1 plus I2 plus I3. Now let us find the individual value of I1, I2 and I3. Okay, so current through R1, which is I1, which according to Ohm's law, what we can say, the total potential is V. So V by R1. Similarly, current through R2, I2, will be equal to V by R2. Current through R3, that is I3, which will be equal to V by R3. Okay, so we found all the 3 currents, and the total current I will be equal to, potential remains same, V. So V by total resistance. So all the resistance are connected in parallel, so I write it as RP. Okay, now we know this. I is equal to I1 plus I2 plus I3. So from there, can I write? We know this, right? So from there, can I write in place of I, V by RP, in place of I1, V by R1 plus V by R2 plus V by R3. Okay, so you see, if you take V common, so this will be V 1 by R1 plus 1 by R2 plus 1 by R3. The V and V will get cancelled out, and you are remaining with Rp equals to 1 by R1 plus 1 by R2 plus 1 by R3. So this is the formula for resistance connected in parallel. So you got 2 formulas for series, resistance connected in series. Equivalent resistance Rs will be equal to R1 plus R2 plus R3 if you have n number of resistances, so on. Similarly, if the resistances are connected in parallel, so 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. We have done combination of resistors. To recapitulate, resistance can be connected in parallel and series. So let us do few sums on that. I have taken down 2 simple and easy sums from the topic. You see, the first question says 3 resistors, 2 ohm, 3 ohm and 4 ohm are connected in series and parallel. You need to draw the arrangement and find the equivalent resistance in each case. So let us do it. So for the first one, when the resistances are connected in series, how we are going to connect them? What will be the arrangement is going to look like? The arrangement will look like series, right? So 2 ohm, 3 ohm and 4 ohm. 2 ohm, 3 ohm, 4 ohm. 3 resistances connected in series. What will be their equivalent resistance? We know the formula is R1 plus R2 plus R3. So this is equal to 2 plus 3 plus 4. That comes to 9 ohm. That is the answer for the first part. Similarly, part B. Part B says we have to connect them in parallel. So how we are going to connect them in parallel? Parallel connection looks like this. 3 resistances connected in parallel. Okay, so first one is 2 ohm, 3 ohm and 4 ohm. And how we are going to find the equivalent resistance? We know 1 by Rp is 1 by R1 plus 1 by R2 plus 1 by R3. So what are we going to get? 1 by 2 plus 1 by 3 plus 1 by 4. If you do the calculation, what you're going to get? 13 by 12. Okay, so this is 1 by Rp. We need to find Rp, right? So Rp is 12 by 13, which is 0.92 ohm. Okay. Finally, we have another question. The equivalent resistance of the circuit diagram is 4 ohm. Calculate the value of X. Okay, we need to calculate the value of X when the equivalent resistance is 4 ohm. For this, the circuit diagram will be given to you. Okay, so what will be the circuit diagram? In this question, the circuit diagram is this. Okay, this is 5 ohm, this is X ohm, this is 8 ohm and this is 4 ohm. Okay, this is terminal A, this is terminal B. You need to find the value of X. You see these two resistors are connected in series. Again these two resistors are connected in series and then they are connected in parallel. So for these two, what you can write down? 5 plus X. So this is 5 plus X, and for these two, what you can write down? The equivalent resistance will be 8 plus 4. So can you rearrange it? Simplify it in this way. This will be 5 plus X, so we'll make it equivalent. One resistance 5 plus X, and here again we'll make it as one resistance, which will be 8 plus 4, that is 12. Okay, now these two are parallel to each other. So when they are parallel to each other, what is the formula? Okay, so what is the formula? 1 by Rp equals to 1 by R1 plus 1 by R2. Okay, so if you simplify it, you will get R1 into R2, R1 plus R2. Okay, so Rp is equal to R1 R2 by R1 plus R2. Okay, what is R1? 5 plus X into 12 by 5 plus X plus 12. This is what it is going to look like. Now if you solve this, what are you going to get? If you solve this question, and yeah, the equivalent resistance is also given to you. This is equal to what? 4. This is equal to 4. Okay, so if you are going to solve this, you are going to get the value of X, which will come as X is equal to 1 ohm. Please do the necessary calculation for the sum and check if your value is coming as 1 ohm or not.